Yeah, good evening, everybody. Myself, Samir Mandal. Okay, so welcome to my this live sessions. Okay, yeah. Till now, whatever vector space we are talking about. Okay, so we was able to find the basis of that vector space, but today I will discuss one special type of vector space. That time we can see that it is little bit difficult to find the basis of that vector space. So do you have idea about some vector space that it is not possible, not almost possible to find the basis? Exact basis, yeah, I'm telling about.
No idea, sir.
At first, please tell me, if I am giving to one vector space, is there is always there is a basis or not? Yeah.
Yes, sir. There is a basis for vector space.
Okay. So is it possible to find every time, is it possible to find the vector space? Sorry, basis of a vector space?
So if vector space is finite dimension, then it's possible.
Yeah, for other cases.
Other case, it's not simply possible, sir.
Could you please give me one example of vector space that finding the basis of that vector space is not possible?
So polynomial, set of polynomial.
Now we already know for basis of set of all polynomials.
So, and
Yeah. What is the this, if you consider this is your polynomial sets? Okay.
So every vector space has a basis actually.
Yeah, I agree. This statement. Every vector space has a basis. My question is it always possible to find that exact what is the basis of that vector space? I know the existence of vector space, sorry, existence of basis of a vector space, but my question is it possible every time, is it possible to find that basis of that vector space? This is my question. Could you understand my statement?
Yes, sir.
Yeah. For if you consider this is your set of all polynomials, okay, then already we have seen that 1 x square xn, this is a basis of, is a basis of, we already proved this statement in my tutorial class. Okay, so today I want to consider one vector space, this very interesting vector space. So before that we are discussing about yeah, we already known about this vector space, I think. What is that, Rn? Yeah, please someone define what is Rn.
so it is a vector space whose element is the form of n tuples.
Yeah, so this is nothing but a collections of like that n tuple or sequence of n number only. Okay, fine. Yeah, so here operation is plus operation, addition and multiplication. These two operation we are already known. Okay, so this is a vector space over R. Okay, vector space over R. What is the basis of that? What is the basis of Rn? Sorry. What is the basis of Rn?
Sir, standard basis.
Yeah, standard basis. EI equal to 0 is 1. This is your ith positions. Okay, next is order 0. This will form a basis for Rn for I equal to 1 to up to n. Okay, it's fine. So
Yes, sir.
this collection will form a basis, is a basis of Rn. Is fine for everyone.
Yes, sir.
Yeah. So now I want to define a similar kind of vector space. Okay, for infinite, definitely infinite. This is a finite dimension vector space. Okay, I am going to define like that. Its notation is R infinity. Okay, what is that? Here we are talking about only finite number of, is a finite number of element was there. Okay, this is sequence of
Yes,
finite number only. Here we will consider the sequence of infinite number. Okay, like a1, a2, sequence of infinite number, or collection of sequence, you can tell. Yeah, is it fine?
yes, sir. In that vector space, sir, each term is a sequence.
Yeah, its
Of in-
term is a sequence. Yeah, everyone understood this definition? Not, please tell me at first.
Yes, sir.
And please tell me what is the operation here. For Rn, use your two operation, additions and multiplications. Okay, what is the operation here for sequence things? This is the collection of all sequence. Okay,
So it will be addition and scalar multiplication only.
yeah, how we can define?
So
Suppose
we
you have,
attempt component wise.
yeah, component wise similar to Rn. Okay, so it has also two operations, additions, multiplication, similar to Rn, similar to Rn. Okay, so here we have seen that this is a basis of Rn. So naturally one can think that generalizations of this one might be a basis of R infinity. Is it or not? Yes, yes. So because this is R infinity is a your generalizations of Rn. So one can think about that this basis also may be we can generalize for R infinity. Okay, so how we can generalize this definitions for R infinity? Please tell me what is the EI for R infinity?
Sir, I goes from 1 to infinity. Is the standard basis.
Now please tell me what
Same.
is the EI element in R
At
infinity?
the ith position,
It's
P1
one
and
at the ith
I
position.
varies in natural numbers.
Yeah, every position are 0, only ith positions are 1, and it will goes to up to infinity. Okay, so naturally this is belongs to R infinity. Everyone agree with me?
Yes, sir.
Okay,
Yes, sir.
so one can think about that. If you take these collections, one can think about that this will form a basis. Is it basis? Is it basis for R infinity?
Yes, it is a basis.
Before that, please tell me, is it a linearly independent set or not? Is it linearly independent? Is it linearly independent? Please, at first, please tell me.
Yes, sir.
How you can prove this one, this statement?
So if you take the linear combination of those vectors no, and equate it to 0, then its coefficients can only take 0. So it will be linearly independent.
Yeah, I agree with everyone are agree with Fernandez? Everyone agree that it is a linearly independent set? Rajesh, do you agree?
So not sure, sir.
Yeah, please try. At first, please tell me what is the definition of linearly independent definition for infinite sets? What is the definition of linearly independent set for infinite sets? I already recall this definition in my tutorial class.
So if you find any set which is linearly independent and
Any set is not any finite set. I will
finite set
take,
is
yeah,
finite.
any finite collections from here, okay, and we will check it is linearly independent or not. Okay, so take any finite collections. Take ei1, ei2, ein. Check it's linearly independent or not. Then we will done. Okay, this is because this is arbitrary collections from here. So you have to try this is linearly independent or not. Please check it as soon as possible. You can easily check because when we are talking about this one plus alpha 2 ei2 up to n equal to 0, what we will get here? We will get 0 at the alpha th position. Alpha 1 position we will get alpha 1. Okay, then we will get alpha 2, like we will get alpha n. Oh, sorry. Yeah, yeah, we will get like that. Okay, and what is the 0? 0 is all component are 0. Okay, so when we are trying to equate both sides, we will get that alpha 1 equal to alpha 2. Is it fine?
Yes, sir. Fine.
Yeah, so we can claim that this is a linearly independent set. We done. So right now we have to check is it a span of R infinity or not? So my next question is this collection span of R infinity or not? Yeah, please tell me. Is this collection is a span of R infinity or not? This is my questions.
It spans, sir.
Spans. What is the definition of span for infinite sets? Please tell me. No. Why? Garg is telling that no. Sin x, but how we can take sin x here? This is your sequence. This is your infinite sequence. Sin x is not there. Yeah.
Sir, we can write any element of R infinity in term of linear combination with the EIs.
Yeah, finite linear combination, not any linear combination.
Okay, finite, sir.
Yeah. So yeah, I'm giving to one element from your R infinity. Every element is one. Definitely, this is a belongs to R infinity. This element. Agree? Every component are one. So definitely, this belongs to in your R infinity sets. Okay. Yes, sir. So could you write this one as a linear combination of finite linear combination of this one? This is my question. Could you write this element as a finite linear combinations of this one?
Yes, it can be written, sir.
Finite linear combinations.
Sir, no, sir.
Because here your
So
ith
infinite
position
it
is,
can be actually.
yeah. So what do you mean by span of any infinite sets? Some sets will be is said to be span of some sets when every element of that sets can be written as a finite linear combination of these sets. Okay, finite, this is a very important words for your spanning sets. Okay, so because when we are taking these sets, only your ith position is 1. Okay, so when we are talking about finite linear combination, so we'll get at finite number of position, we'll get finite number, otherwise all are 0. But if you look at this one, every place has 1, some non-zero, every place has some non-zero number. But when we are thinking about the finite linear combination of ei, that time we are getting that only finite number of positions are non-zero. So is it possible to write this element as a finite linear combination of ei?
No, sir, it's not possible.
Everyone agreed?
So it is not possible.
Yeah, Risu?
Yes,
Risu,
sir, agree.
sorry?
Sir, agree.
Okay, Vishal, are you agree? Okay, so this element we are not writing as finite linear combination of ei. So this is not a basis of,
Acı eksemez.
yeah,
What
is
do you my
not uh, basis of R infinity. Okay, so next one can think that it is not a basis of R infinity. Okay, so we want to add this element. Is it again? So take this is V. Okay, yeah, take this B. So one can think it is not a basis of R infinity, so we want to add this element. Okay, because this is a linearly independent set. Okay, so this is your linearly independent set, so we can extend it to a basis. Okay, so this is this element we can add with this one. Okay, so right now you can check that this is a linearly independent set. Okay, linearly independent set. So my question, next question is it a basis of R infinity? At first, are you agree with me? This is a linearly independent set or not?
Yes, sir, linearly independent.
Because this element can't be write as a finite linear combination of EI. So this set will form a linear independent set. So my next question is it a basis of R infinity? Is it a basis of R infinity? This is my question.
No, sir.
Why?
If we take another element from R infinity and
Which element?
uh,
Please tell me precisely. Tell me one element.
So if you take the element which is other than that 1, 1, 1, then it will this not form that linear combination.
Yeah, please tell me one element.
so like 1, 1, 1 up to
If you take 2, 2, 2, then it will not form.
Yeah, every element 2, 2, 2, 2. Okay.
yes, sir.
Yeah. So it is belongs to your R infinity, but it can't be expressed as a finite linear combination of this one. Okay, it can't be expressed. It can't be expressed as a finite linear combinations of so it is not a basis of it is not basis of R infinity. So my next question is it possible to find a basis of R infinity? This element we can't add with this one because this one and this one are linearly dependent, so we should take this one. 1 2 3 4. Okay, if you take this one, this is belongs to your R infinity. Okay, and this is also we can't express as a finite linear combination of these sets. Okay, and 1 to infinity union V. Okay, if we add this one, okay, this is take this is U, okay, union U, okay, this will form union V, union U. Again this will form a linearly independent set, okay. Are you agree? This is a linearly independent set.
Yes, sir.
Yes, sir, it is linearly
Yeah,
independent.
but again you can construct one example from R infinity that it will not form a basis of R infinity, okay.
Sir.
Yeah, so can you find a basis for R infinity? If you go with this process, okay, this process will not be end, okay.
So
For
we can't find.
yeah, so for this case is it
So
is
basis will be R infinity itself.
yeah, so it's the obvious choice. No, how can you tell that R infinity is a basis? Because uh, these two are 2, 2, 2, 1, 1, 1. These two are in R infinity, but both are linearly dependent. So in basis,
Okay.
yeah. So is it possible to find a basis of R infinity? This is my question. Is it possible? Is it possible to find a basis of R infinity? This is my question. Yeah, basically this process will go continuously. This process will not be end, okay, if you try to think properly. So for any countable sets can be basis of R infinity at first, okay. And this is not possible to find a basis of exact basis of R infinity. This is also, we can say, it is not possible to find a basis of R infinity. Not only for R infinity, there are proper power subspace of R infinity. Is it no, for this case also not possible for find the basis of R infinity, okay. Yeah, so take one subspace of R infinity, all convergence sequence, okay. Take all convergence sequence, yeah, okay, collection of all convergence sequence, collection of all convergence sequence, okay. This is your one collection. Yeah, take this one. So one can check that this is a subset of R infinity. Are you agree?
Yes,
Yes,
sir.
sir.
Yeah, so one can check that this is a subspace of R infinity also. This will form a subspace of R infinity, these collections. Are you agree this one?
Yes, sir. I agree.
Okay, so my next question is so your this one, this belongs to your these collections. Please give me one name of this, take C, okay. this belongs to your C, all convergence sequence. Are you agree? Only one term is non-zero. Definitely this is a convergence
Yes.
sequence. Yeah. So this is belongs to C. Okay. So is it basis this one? Is a basis of C? This is a basis of C or not? Please tell me. Yeah, same problem arising. I agree with your statement. Please give me one particular example. Please give me one element from C which can't be written as a finite linear combination of EI. Please tell me one arbitrary example of convergence sequence.
So you can take 2 plus 1 by n, the sequence 2 plus 1 by n.
Yeah, or 1
That
by n also we can take 1 half 1 3. Yeah, this one. Okay. So definitely this belongs to C. Okay, but since every position are non-zero, so we can't write this element as a finite linear combination of this one. Okay, so this is not a basis of C. Okay, so for this case also it is difficult to find, not difficult, it is not possible to find a basis of C. Okay, right now I am taking another subspace of R infinity. This is very interesting subspace. Okay, take I forgot the notations, whatever, some notations. Take these collections. Okay, A1 A2 AM. Okay, after that all elements are 0. Okay, after a finite stage your finite number non-zero element will be there. After that every element will be 0. Okay, understood these definitions?
Yes, sir.
Yeah, all element can be 0, one element can be non-zero, every element can be 0. This is also possible, but all element can't be non-zero. Okay, after your finite stage, finite number of stage, every element should be 0. Okay, this elements is belongs to all 0 are there. Sorry, to give the name of, sorry, give the name of this sequence at the 1 minute. I am checking, I forget the notations. Okay, take V. Otherwise I don't know, the I forgot the notations. Take V. Okay, so this is 0 is also belongs to V, 1 all other 0 is also belongs to V. Okay, your EI also belongs to V, because your ith position are 1, after that all are 0. Definition of these sets is after a finite number of stage every element should be 0. Okay, every element must be 0. Okay, so this is your definition of these sets. Okay, so all are 0 is belongs to B is fine. From your first position to everything at 0. First position is non-zero, everything at 0 is possible. your your second position are 0, first second position non-zero, first 0, after that all are 0 is possible. Okay, after a finite number of stage every element must be 0. This is your definition of B. Okay, you can check that this is your subset of R infinity. Okay, and V is a subspace of R infinity. Are you agree?
Yes, sir.
Yes, sir.
Yeah, it is obvious. Okay, so you can check that this is a basis of V. You can check. Yeah, are you agree with this statement or not? Please tell me.
So EM plus 1 and EM plus 2 up to that, these elements will not belong to the set, no?
Sorry, please tell.
So the element this EM plus 1, then EM plus 2, those will not belong to the set.
Why? Em plus 1 you are taking. So
Yeah.
m plus 1 is 1, after that all are 0. So m plus 1 is your finite sets. M plus 1 is finite number.
So isn't it this way? So after M, like after M position, it is 0.
Sorry?
So isn't the element like this? After the M position, all the elements are 0.
Yeah. So my definition of V is after a finite number of stages, it can be n, m, k, l, no issue. After a finite number
Okay.
of stages, all are 0. This m is not particular.
Okay.
If it is particular, then we can send. We can say anything. Okay. That time it will not form a vector space also. Yeah. Okay. So m is not fixed here. M is this notation is for finite number. Okay. This notation is index the finite number only. So after a finite number stage, all are 0. Okay. So em plus 1, sorry, em plus 1, sorry. So your em plus 1, em plus 2 all are belongs to these sets. So are you agree with this statement that this is a basis of V or not? Please tell me. Yeah, take one arbitrary element from V. I am taking one arbitrary element, okay? A1.
So it forms the basis of V.
Yeah, how?
So if you take any element from V, then any element can be written as finite linear combination.
Yeah, because we can, yeah, take your E1, E2, E2, AK, EK. After that all are 0. Okay, 0 into EK plus 1. Okay, we don't no need. This is, yeah, this is enough. All are 0. Okay. So this element can be written as a finite linear combination of EI. Okay. This will form a basis of your V. Okay. So we start with R infinity. Okay. This is a collection of all sequence. For this will not form a basis of R infinity. Okay. And also this is not form a basis of your set of all convergence sequence. Okay, but this is form a basis of your these sets. Okay, so for R infinity set of all sequence and set of all convergence sequence, it is not possible to find a basis of that vector space. Okay, sometimes it is too difficult to find exact basis of that. Not only too difficult, we can't find that basis of that vector space. Only we can give the guarantee the existence of basis. Okay, I will tell you another example, then I will go for proof of that every vector space has a basis. Okay, yeah, yeah, take real number. Please tell me, is it a basis vector space or not? Real number over the field q, is it a vector space? Here is a field is q. Okay, your R means real number over R. Okay, the real vector space of real number over the field R. Here I am taking the field as a q. Okay, set of all rational number. Is it a, do you have any idea about that? Is it a field or not, q? Risu, do you have any idea?
Sir, I think it is a field.
Okay, Fernandez, q is a set of all rational number. Set of all Rajesh, are you agree?
Yes, sir, is form a fields.
Fernandez,
Yes, sir, it is a field.
field. So is it a vector space or not? R over Q. Is it a vector space?
Yes, sir, it is a vector space.
Okay, this is your homework. Please check that this is a vector space. Okay. Is you agree?
Yes, sir, I am agree.
Okay. So I am going to please tell me one linearly independent set of here. Every you can take, you can tell that one non-zero element. I am agree. So please tell me one infinite linearly independent sets here, because your R over R is a vector space of dimension 1. Okay, so yeah, sorry, my first question is it a finite dimensional or not? R over Q is a vector space, I agree. Okay, so is it a finite dimensional or not? This is your dimension 1. Okay, this dimension of R is 1. Okay, when we are talking about R over R. Okay, Vishal is telling about that infinite dimensional. So when you are telling that this is infinite dimensional, please tell me one example of infinite linearly independent sets. Give me example of a infinite dependent sets. Okay, one interesting example is there. everyone. Yeah, Vishal, I'm agree. Okay. Vishal is telling about that one pi square. Okay, this one, and I was telling about this one 1 root 2 root 3 root 5 square root of all prime number. I will we can start with root 2 also. I am starting with 1. Okay, after that we are taking square root of all prime number. Okay, root p, where p is your prime. Okay, so 1 root 2 root 3, 1 is your not a prime number, but still I am including 1 here. Okay, oh my god, what is this? Okay, yeah, 1 root 2 root 3 root 5. Okay, square root of prime number, and 1 pi square. You can take also this collection, you can take also this collection, whatever. Check, this is a linearly independent set. Okay, so this is your homework. Check that it's a linearly independent set. So one can easily say that from these two statement we can say that R over Q is not a finite dimensional vector space. Okay, from because this is your linearly independent set, this is your linearly independent set, both are infinite, so R over Q is not a finite dimensional vector space. Okay, so for this case also it is not possible to find the basis of R over Q. Okay, so yeah, do you have any idea about how to prove that every vector space has a basis? Every vector space has a basis. Okay, this is the guarantee the existence of basis, but sometime we can find, okay, the basis of a some vector space. Okay, till now the what is the scenario is going on, it is understood or not?
Yes, sir, understood.
Please tell me, what was the scenario of my today tutorial class?
It is not always possible to find a basis for infinite dimensional vector space.
Yeah, but existence, there is a guarantee of existence of basis. Okay,
Yes, sir. Yes, sir.
yeah, do you know how to prove this statement that every vector space has a basis? If finite dimensional, then we done, because we will start with one non-zero number. One non-zero number is a one singleton non-zero number is a linearly independent set of that vector space, and after that we'll add another vector space who is not a linear combination of that one. Will go continue after a finite number stage, it will stop, and that set will form a basis of that finite dimensional vector space. For finite dimensional vector space we done. Can you repeat this process for infinite dimensional vector space, that will start with a non-zero number and will reach to a basis? Is it possible? For a finite dimensional vector space, if someone start with a non-zero number, then we can reach to basis. Is it possible for infinite dimensional vector space to reach a basis with starting with a non-zero number?
Not always, sir.
No, this is also possible. Possible means we can give the existence of, guarantee the existence of basis, but which one we can't tell. Yeah, using this same process we can't find the basis of infinite dimensional vector space, but using this same concept, okay, we can give the guarantee of existence of basis. Okay.
Okay, sir.
Yeah, for finite dimensional case we are with starting with non-zero number we are getting the exact basis, but for infinite dimensional vector space we will start with a non-zero number, but we'll go through the same process. Okay, not exact same process but like that same process, and we'll give the guarantee of existence of basis. Okay, so do you have any idea about proof of that statement, how we can go? Fernandez, do you have any idea about how?
No, sir, I don't have any idea.
Vishal, Rishu, do you have any idea?
No, sir.
Or everyone are familiar with John's lemma? Everyone are familiar with this statement, this lemma? Basically, here we have to use the John lemma. Okay, this proof is very simple. If one know the what is the John's lemma, using this lemma, you can prove that every vector space has a basis. Do you know this statement? This
No,
lemma?
sir, I don't know about it.
Okay, so today I will not go through this proof. I can go through this proof, no issue, but you should know about that. What is a? Do you have any idea about what is a partially ordered sets?
Yes, sir.
Okay, everyone are familiar with the partial order sets?
Yes, sir.
Risu,
No, sir.
Vishal,
I don't, sir.
okay. So I am telling one particular form of John's lemma, okay, for inclusions, using inclusions for sets, okay, and you can search in Google and yeah, and read the what is the exact John's lemma. Okay, I am telling one particular form of this John's lemma. Okay, take A as an your arbitrary sets. Okay, and take C is the collection of all subsets of A. Okay, C is the collection of all subsets of A. Okay, so now I am considering this collection. S1 is a this is your inclusion. Okay, because means S1 is a subset of S2. Okay, S3 like that. We can take these collections. Okay, no issue. Are you agree? This is your collection of all subsets of A. Okay, yeah. So right now I am taking the collection this one. S1 is a subset of S2, S2 is a subset of S3, S3 is a subset of S4, like that. I am taking one collection. Can we take this collection from C?
Sir, S1 is a proper subset of S2?
You can take proper, non-proper, no issue. Take subsets. Okay.
Oh, okay, sir.
Yeah. If you take all are same, then it's nothing. Uh, okay. Then this will all always this will be same. So can we take these collections from C? This is my questions.
Yes, sir.
Yeah, because this is a inclusions notation. Okay, so S1 and C is a collection of all subsets of A. Okay, all subset is there. So suppose this is your singleton set A1. So for S2 you can take A1 A2, for S3 A1 A2 A3. So anytime we can take this collection from C. Okay, so right now I am going through one assumptions. I think everyone are familiar with chains. Okay, this is your form a chain of C. Do you agree?
Yes, sir.
Yeah, I am not going through the exact John's lemma because these were not familiar with partial order sets. Okay, but these are similar things because when we are talking about the inclusions things, that time we know that one arbitrary sets with inclusion, this is a partial order sets. Okay, and everyone are know that this is a chain. So when we are taking that S1 is subset of S2, S2 is a subset of S3, like that when we will go through these things, everyone will know that this is a chain. Okay, right now I am going through one assumptions. If when we are taking this type of collections, when we are taking this type of collection, arbitrary collections or arbitrary chains, our assumption is that union of this one, union of this one is also belongs to C. This is our assumptions. Okay, assumptions AS is PA. I take assume is, this is our assumptions that when we are taking this type of arbitrary, this type of collections, and union is also belongs to C. This is our extra assumptions. Okay, A is your arbitrary sets. We start with arbitrary sets. After that we consider one set C, the collection of all subset of C. This is your, this we are taking one arbitrary chain. Okay, our assumption is the union is also belongs to C. That time your John's lemma guarantee that, okay, what is John's lemma guarantee? That C contains a maximal element. John's lemma, okay. Oh my god. John's lemma says C contains a maximal element. Okay, okay. When we will start with one partially ordered sets, here your arbitrary sets, okay, with inclusion, this is from a partially ordered set. When we will start with a partially ordered set and we will consider arbitrary chains, and union of these things means upper bound of these things is belongs to your C. Okay, that time George lemma say that C contains a maximum element. Understood this statement or not? Please tell me.
Yes, sir. Understood.
Yeah, for your arbitrary set, this union is always belongs to C. Always, this is for set inclusion. This is not our assumption, but for arbitrary setup, for when we will start with a one partially ordered sets. Okay, this should be your assumption. But when we are talking about one arbitrary sets, one a collection of subsets of C with inclusions. Okay, that time this always belongs to C. That time this is not a, just that time this is not a assumptions. For when we are talking about arbitrary set with inclusions, okay, that time this is not a assumption. But for your arbitrary partial order set, okay, with some relations, one set with some relation, if satisfy some property, then we will set the partial order set. If for partial order set every chain has a upper bound, okay, if every chain has a upper bound, that time George lemma says that that collections contain a maximum element. This is John's lemma say. The statement of John's lemma. Everyone understood or not? Please tell me. Fernandez?
Yes, sir.
Risu?
Yes, sir.
Okay. So right now I am going to the proof of this statement. that every vector space has a basis. Every vector space has a basis. Please tell me someone that how we can use this John's lemma. Please try to think. Similar to your finite dimensional vector space. Yeah, start with one non-zero element. Okay. Yeah, take your V is a vector space. Start with a non-zero element. This is your really independent sets. Okay. Please try to think. This is not right now. You should give the answer because you know the John's lemma and you know how to go through for finite dimensional vector space. We go through the similar process. Your root are same. Okay. You have to you already know that you have to use the John's lemma. So John's lemma, what we did, we take one collections. Okay, in John's lemma we took one collections. Okay, so please tell me what will be the collection for this one.
So you can take collection of linearly independent
Yeah,
sets here.
very good. Yeah, see. Okay, collection of dependent sets. Then we have to check that every chain has a upper bound. Okay, you have to check this one. Okay, okay, so I am taking one chain that s1 is subset of s2. Yeah, this is your chain. Okay, and here every element is linearly independent. What is the upper bound of this one? Union of this one. Is it a linearly independent set or not? If it's a linearly independent set, then this union is belongs to your C. Okay, so my question is it linearly independent set or not? This is your arbitrary chain. Okay, and this collection with inclusion form a partial error sets. Okay, this collection with your inclusion form a partial error set. This is your arbitrary chains. What is the upper bound? Upper bound is a union of Si. My question is it a linearly independent set or not? If it is a linearly independent set, it will belongs to C.
Yes, sir, it is linearly independent.
Independent set. Union of linearly independent set is linearly independent. So this is a linearly independent set. So your union is belongs to C. So by John's lemma, we say that C has a maximal element. Okay, take M. Let M is a maximal element of C. Yeah, yeah. But your claim, our claim is M is the basis of your what V. Okay, this is my claim. Yeah, please tell me how we can prove. Yeah, goes through with contradictions because already we know that this is your maximal linearly independent maximal element of C means maximal linearly independent sets. Okay, goes through the contradiction method. So you have to find another linearly independent set which is bigger than M. Okay, so take if your M is not a basis of V, then what will be happen? Please tell me. Yeah. Suppose your M is not a basis of V, then what will be happen?
Sir, then it won't generate the complete B, no?
Yeah.
So there will be certain element uh, which is not present in B.
Present in?
I mean, if it is not a basis, then there won't be certain there will be certain element of B which cannot be generated by this.
Yeah, understand. Yeah, fine. After that, yeah, you are going through correct direction. Please tell me after that. Take that element with M union that. The second linearly independent set. Is it or not?
Ah, yes, sir. Correct, sir.
Yeah, so we are getting another linearly independent set. Okay, and which is the superset of M. Okay, so this is a contradiction that this M is a maximal element. Okay.
Yes, sir. When M is a maximal element, we should not have any superset there.
Yeah. So
But we are getting, so it is a contradiction.
yeah, everyone are agree with me?
Yes,
Rajesh,
sir, agree.
Yes, sir, I agree.
Risu,
Yes, sir, I agree.
Vishal. Okay. So do you have any question? Here I am want to stop. Please tell me if you have any questions. Okay.